So just looking at this, remember the difference between a strong electrolyte, weak electrolyte, non-electrolyte is just how many ions are formed. So in this first one, this shows if you have a strong electrolyte, that means that you make lots of ions. So I always just think like as soon as you put this in water, it's going to form ions 100%. So one thing to notice that the arrow goes in one direction from left to right. So that tells you it completely forms ions. 2, there's ions, positive and negative charges as the products. So that's really the easiest way to identify if something is a strong electrolyte. I don't know why they didn't put the AQ, but there really should be an AQ after the chlorine. I don't really know why it's not there, but it should be. And notice in this one, they actually balance the equation. When you go to balance this equation, it's only ever going to be the product side that you'll have to add a coefficient to. So notice the magnesium chloride is MgCl2. So that means there's 1 magnesium and 2 chlorines on the reactant side. So do you see on the product side, the Mg plus 2, there's just one of them, right? So there should be like a little 1 in front of them. One of these needs to have 1 magnesium ion on the product side, but then notice the 2 in front of the chloride ion. So having this 2, really, this is what it started doing now. There. This 2, remember, it would not zoom. Now it's learning the random zooming. 3 more weeks. Serenity now. And now it's, maybe it's because of the weather. I'm going to blame it on something. There. Now my little cursors come back and I've disconnected. Okay, so if you look in front of the chlorine, the reason that it's got that 2 in front of the chloride ion is because the formula of MgCl2 means that it needs to have 2 chloride ions in order to be balanced. There. So can you see those? So if you have to balance it, it's only going to ever be the product values that you're going to have to change. You're never going to change the reactant side. It'll only ever be the product side when they split into those ions. But if it's a non-electrolyte, notice 1, the arrow goes left to right. So that's like a strong electrolyte. So 1, we have arrows, the arrow goes one direction, but 2, no ions. The reactant is written exactly as the product. You just change it to AQ, which means it's aqueous. So that just tells you that it's dissolved. So remember, we mix ethanol in water, no electricity. When we put sugar in water, no electricity. So those non-electrolytes, they dissolve because they have the same intermolecular forces that water does. So they can dissolve. They're both polar. So they can mix with water, but they don't form ions, which is the reason why they can't carry electricity. Okay? And the other nice thing with this, you never have to balance this, right? You never have to split it up. You just take the reactant and write it on the product side, just change it to AQ. So it's pretty straightforward. Third one though, weak electrolyte, you can identify the weak electrolyte by the arrow. So see how the arrows go both directions? That's different from either of the other 2. So when you see that, when you see the arrows in both directions, that's how you know that's a weak electrolyte, because remember that I told you that like 95% of the molecules do not form ions. A very small percentage do. So this means in that beaker, the vinegar beaker, what this one is, the vinegar beaker, when we put it on the little light bulb apparatus, it barely glowed, because there's just a little bit of ions formed, enough to carry the current, just enough to make the light bulb be very dim. But it does form those ions, so you would split it into those ions. And I'm not going to ask you to complete a reaction, but if I gave you the examples and said, which is the strong electrolyte, you should be able to pick it out. Which is the weak electrolyte, you should be able to pick it out. Okay? Which one's a non-electrolyte? Those are really the criteria to look for, is you'll see arrows in both directions with the weak electrolyte, and you'll also see that ions are formed. And just remember, you don't have very much ions formed in that. Okay? All right. So, in the middle part of this chapter is talking all about solutions. And it's all the math. So if you don't have a calculator, you want to come up and get a calculator. If you didn't grab a periodic table, you need a periodic table. If you didn't grab the little half sheet that I have up there, make sure that you come up and grab the half sheet before we start, because you're going to need all of those for this. So when you think about concentration of something, it's how much you have in a sample. So you can have a 1% salt solution, a 10% salt solution. You can have a 25% salt solution. You can alter the amount of the solute in a solution. Remember when we were talking about solutions, how you can have a little bit or a lot. You can like dissolve the maximum possible, or you might have it with less than the maximum. So in concentration, just wait. So in concentration, remember that what's in the denominator is always going to be the amount of your solute, the thing that's dissolved. What's in the denominator is always going to be the amount of your solution, not just solvent, but the solute and solvent combined. So that's going to be both. And that's probably the one thing that people get kind of mixed up, is they think it's the amount of solute divided by the amount of solvent. It's actually the amount of solute dissolved in the entire thing. So that includes solute and solvent. So there's a couple of different ways that we can talk about this. The first one is used very commonly in chemistry because it is based on the amount of moles of a substance. So it's really relative to the formula of the substance rather than just talking about a general amount of it. So that is called molarity. So you might have noticed in lab, like last week, we used 0.1 capital M HCl. So if you looked at your periodic table, if you looked at that Erlenmeyer flask that you had on your lab bench, this is like what my pen would work. This is what it looked like. So it was 0.1 M, capital M, and then HCl. That capital M stands for molar. And it stands for a value molarity. The capital M means moles per 1 liter of solution. So this is kind of like saying a percent, kind of like saying a dozen. Like a dozen, you have to, if you're going to do anything using like 2 dozen, 3 dozen, 5 dozen, you have to do the math in your head and convert it back into what it represents. So moles, molarity is the same thing. Anytime you see the capital M, just go back and substitute whatever the number is in front. So this would be the 0.1 moles per 1 liter. So that's what that number represents. It's really just a short way of being able to write it. Grab all that. So if I have 3.4 molar NaOH, that means that I have 3.4 moles per 1 liter. Just take and convert that capital M to what it represents, and then you can use it because now it has units. So when you go to use molarity, you've got to figure out, okay, what am I given? So if you're given molarity, that's concentration. Concentration, as kind of a general rule, if you take the concentration of a sample and multiply it times the volume, that will tell you the amount of your solute. Concentration times volume equals the amount of your solute. So in this one, in lab, we made soap and we mixed a fat or an oil with 40 milliliters of 6 molar NaOH. So the question is, 1, how many moles of NaOH is this? And then 2, how many grams would that be? So when you see that capital M, the first thing to do is change it to what? You want to put it back into, so this is my concentration, right? Molarity is concentration, and here's volume. I can multiply concentration times volume to figure out the amount of the solute, which is sodium hydroxide, but I've got to make sure that, 1, put your units how they need to be, so 6 big M, 6M NaOH, that is just saying 6 moles of sodium hydroxide, NaOH, divided by 1 liter of the solution. So I can take this concentration times the volume, but do you see that my units are in liters in molarity, and my volume example is 40 milliliters. So I cannot multiply liters and milliliters. That's like multiplying quarts and gallons. I've got to make sure that I put the units in the same. They have to have the same value. So I've got to take 40 mLs, and I need to convert it to liters. And that way I can multiply them in liters, and liters will cancel. 40 ml times in a line. It's always just going to be a single unit conversion when you do these. Milliliters on the bottom, liters goes on top. Milli gets a, if you put in front of milli, the millennium means what? 1,000. So milli gets the 1,000. Liters gets the 1, right? The base unit gets the 1. Anytime you have milli, 1,000 goes in front of it. So in doing the math for this, you're going to take 40 and divide it by 1,000. So it comes out as 0.040. Right? Decimal place goes to the left by 3. So now I can multiply this. So I can multiply the concentration times the volume. What happens to liters? See how these will cancel. Liters and liters are going to cancel, and it's going to tell me the number of moles of sodium hydroxide. Concentration times volume can allow you then to figure out the number of moles of sodium hydroxide. So 6 times 0.04 is? So 0.24. 0.24 moles. Then the last question, how many grams is this? So if I have 0.24 moles of NaOH, and I want to know how many grams it is, what do I need to know? How do I go from grams to moles or moles to grams? I have to use the if you have moles to grams, grams to moles, I have to have the formula mass. Remember NaOH, NaOH. What is the mass of sodium? Look on your periodic table, find the atomic mass, round to the whole number. So it would be 23. Oxygen, 16. Hydrogen is 1. So I just add those all up. 23 plus 16 plus 1. This tells me that there's 40 grams in 1 mole. I just add the mass of each of the atoms in the formula. And now I can set this up in just another single step, just like a unit conversion. What unit do I put on the bottom? Moles. The answer that I've got, 0.24 moles. So remember, moles would go on the bottom. The answer I want is grams. So according to the formula mass, there are 40 grams in 1 mole. So mole gets the 1. Grams, there's 40. So I take 0.24 times 40. 9.6. So this actually tells me exactly how much sodium hydroxide was in that solution that I added to the fat and oil, then cooked and stirred to get it to thicken and actually become soap. Okay, so if you're given a concentration and a volume, if it's in molarity, just put the capital M to what it means. Make sure that the volume units are the same. They've both got to be liters. Then you can just multiply them. That allows you to find moles. If it asks for moles, then you're done. If it asks for grams, then you need to go one more step, find the formula mass, and figure out how many grams in 1 mole of whatever that compound is. So you try this one. 88 grams of sodium chloride is mixed in water to make a final volume of 0.75 liters. What is the molar concentration? So what am I trying to find here? And so what's the units going to be for that? Moles per liters, right? So the molar concentration, I'm trying to find that big M. So I'm trying to find how many moles per 1 liter, right? So see, it's the solute divided by solution. Do you know the volume? Yes, it's 0.75. So I already know this is going to be my volume. Do I know the number of moles? No. What do I know? I know the mass. And I can go mass to moles, right? So I can go grams to moles, just like moles to grams, like we did in the last one. So if I start with this, I'm going to have to take the mass of the sodium chloride, convert that to moles, and then I can use it, taking moles divided by the volume in liters, that 0.75, and that'll tell me the molar concentration. So 88 grams of NaCl times in a line. What unit will go on the bottom? Grams. What do I want to find? Moles. So moles will go on top. So I'm just doing it's just a single step. In order to fill that out, I need to know what is the formula mass. So look at your periodic table. Formula mass, we said sodium weighs 23. Does everybody see that one? Chlorine weighs 35.45, but you round that to 35. It's less than a half. So see, it's 35.453. Round down. Don't round up. So since the decimal's a 4, so I just round down. Now I just add them. Add those two together, and that is 58. So there's 58 grams in 1 mole. The formula mass tells you how many grams in 1 mole. So I have 88 grams. So when I go to solve this, what do I put on the top? Moles gets the 1, right? Just like our formula mass says. Grams gets the 58. So you're either going to have to multiply or divide by the number of grams in 1 mole, depending on which way you're going. This one's going grams to moles, so I have to divide. So if I take 88 and divide by 58, you get? Yep, a whole lot of numbers. Okay, 1.5172411379. And that would be moles, because you see that grams and grams would cancel. Everybody got that? So don't want to round that, because I have to divide this number by what? I want to know molarity. I got to divide it by the volume. So what's my volume? 0.75 liters. And it's in liters, so I don't have to change anything. So if you're given the mass amount, you've got to find the moles, and then just divide it by the volume. Make sure your volume's in liters. So just take this number, this 1.5172411379, and divide it by 0.75. And it comes out as 2.022988506. And this would be the big M, NaCl. That's the molar concentration. The number of moles in the sample divided by the volume of the sample. Can I keep all that? No. So I need to round. How many significant figures in 88? 2. How many significant figures in 0.75? 2. So remember, those are the criteria where you figure out rounding, and don't round till you get all the way to the end. So if I'm going to keep 2, what would my answer be? 2.0. So 2.0 molar NaCl is what you would call that. So if you're trying to figure out a molar concentration and you're given a mass amount, convert grams to moles, and then just divide it by the volume. Make sure that you divide by the volume of your solution. Don't just divide by per liter. This is divided by 0.75. So it's sort of like a two-step thing. Convert grams to moles and divide by your volume. All right, try this one. This one I'm giving you the formula mass because glucose is C6H12O6. So just to simplify it a little, I gave you this. That is because 6 carbons is going to be 72 grams, 12 hydrogens. Each of them weighs 1, so that would be 12. And then 6 oxygen. Each one of those oxygens weighs 16, so that would end up being 96. So if you add those all up, you should get 180. So that's where I got that. The formula mass for glucose, just each atom, its mass times the number in the formula, and just add them all up. Right? So everybody remember that. So that's that formula mass, how many grams in 1 mole. So I want to know how many grams of glucose is in a 3-liter solution that has a concentration of 0.65 molar. Kind of like 2 steps to this one. So what's the first step you wanted to solve for in this? Find the number of moles of glucose. So how did you do that? What did you put down first? Changing 0.65 to what? So 0.65, capital M, change that capital M to what it means, because you can't really use it as capital M. You have to change it to what it means, which is 0.65 moles per 1 liter. Right? That's just what the big M, the capital M means. Now I multiply it times what? Times 3.0 liters. So do you see that liters and liters will cancel? So 0.65 times 3 tells me the number of moles. Concentration times volume tells you the number of solute molecules. Now that I know moles, I want to find grams. So the last conversion I have to do is take that 1.95 moles times in a line. What do you put on the bottom? Moles on the bottom. Grams goes on top. Grams gets the what? 180. Moles just gets a 1. So you're going to take that 1.95 and times it by 180, and that would be 351 grams. See how moles and moles will cancel. So concentration times volume, and then if you have to, convert moles to grams. Is that your final answer? Do you have to do anything else?
Yeah.
What? Got to round, right? So if I look up what are my measured numbers, well, 3.0 liters. So that has how many significant figures? 2. 0.65 has 2. So that means this, I can keep the 3 and the 5. What happens to the 0 or to the 1? It becomes a 0. So this would be 350 grams of glucose. Okay, remember I'd have to keep that 0 because 351 would not round to 35. Okay, 351 rounds to 350. I would drop that. There's only 2 significant figures in 350, but it's close to what my final number is. Okay, so we'll do one more. How many grams of sodium chloride is in a 2.5 molar sodium chloride solution if the volume is 750 mils? And so the sheet that I gave you, the very first, the front kind of side of it, kind of gives you the sort of things to follow, I guess, in concentration. So remembering concentration times volume tells you the amount of your solute. So that'll really work for percent solutions or work for molarity. You just have to remember what that capital M means and always convert it back to what its unit values are. So where you see that capital M, just change it to moles per liter. It's 2 steps in this one. 1, I need to find the number of moles. And then 2, I'm just going to take moles and convert it to grams. Just as a note, because molarity is always moles per liter, if you have any volumes in milliliters, always change them to liters, because that way they're the same. So you can use them, multiplying them, dividing them, but units will cancel correctly. Did you solve the first part? Trisha, did you find the first part? What did you do to find that?
Well, first I did the milliliters to liter.
Good. Okay. So took the 750 mils times in a line, 1,000 milliliters in 1 liter. So that ends up changing that to 0.75 liters. So take the volume. If you have any volumes, this is a good note to self. Any volumes in milliliters with molarity, change them to liters. Okay. So now what did you do?
I did 2.5 moles of NaCl over 1 liter times the 0.75.
Yep. Okay. Concentration times volume. Liters and liters will cancel. 2.5 times 0.75 is 1.875 moles. So that's that first step, okay? Convert any volumes to liters, then just multiply the concentration of molarity times its volume to figure out the number of moles of NaCl. Now I need to know with NaCl, to go to grams, I've got to know what the formula mass is. And we actually calculated this on a previous one. Remember that sodium is 23. It's that number underneath the symbol, round to the nearest whole number. Then the mass of the chlorine, rounded to the nearest whole number, added them together, and we get 58 grams per mole, right? Or 58 grams equals 1 mole. 1 mole is 58 grams, however you want to do it. So in this, 1.875 moles times in a line, what unit would you put on the bottom? Moles goes on the bottom, grams goes on the top. And if you do it this way, if you like write it out instead of just randomly multiplying or dividing it, you will never make the mistake. Like kind of keeping those units can help you in making sure that, see that moles and moles will cancel. Moles will always get the 1, and grams is going to be the formula mass. So that's going to be the 58. So 1.875 times 58, and I got 108.75 grams of salt. Can I keep those 5 significant figures? No, I got to round it to what? To 2. Does everybody agree? Up here, 2 significant figures, 2 significant figures. So my answer needs 2. So remember, all that you do is start from the left, underline the first 2 significant figures. The next number's an 8, so what's that going to do? Round it up. So this would be 110 grams of sodium chloride. That 0 at the end, no decimal place. That 0 in 110 is not significant. Those 2 1s give me my 2 significant figures. Okay, so on the back of this sheet, I did a couple more practice problems. One of them is a molarity question, okay? I actually did like a 15-minute solving all the ones that are on the back, so I'm not going to cover them. I suggest that you go through and practice those. If you get stuck, you can watch, like I did all of those questions in 15 minutes. So you could sit down and try to do them all yourself, and then that way, it's a YouTube video, so you can just jump through and find the answers. You don't have to watch the entire thing. If you think you got it right, just kind of jump through till you see the answer. If you get it right, jump through till you get the next answer. But if you get them wrong, then that way I sat down and like wrote it out just like this. So you can sit down and like watch sort of the steps again to help make sure that you've got these ones straight. So percent, people are a little more sort of comfortable, I guess, with percent because you know a percentage is always out of 100. You get an 80% on a test, that's 80 out of 100 possible points. So percent in solutions is always the amount of your solute divided by the amount of your solution. But what's kind of nice is it's never has moles. It's always either going to be grams or milliliters. There's actually 3 ways we can talk about percent. So you could talk about a solid solute and a solid solvent. So if you mix 2 solids, like how they make steel, okay, so in order to make steel, you have to take iron, they take aluminum, they take zinc, and some copper. It all gets heated until it's like molten. The highest concentration metal, that's the solvent. All the other parts of metals, those are the solutions. And so those, they would be mass divided by mass. So that is an M to M. So if you see this, this just means that we have how many grams of solute per 100 grams of the solution. So it could be a mass to mass ratio. So if we had, so say that we had a 3% copper, and it's a mass to mass, that would just means that I have 3 grams of copper per 100 grams of the mixture, right? So we'll just say it's a solution. So that would be mass to mass, grams to grams. You can also have volume to volume. If it's volume to volume, then that means my solute to liquid and my solvent's a liquid. So I'm mixing 2 liquid things, or I could be mixing 10 liquid things. But the idea is my solute is a liquid that gets added to a liquid sample. So like the ethanol that I did in lab. So when I mixed the ethanol, I mixed it with a little bit of water, stirred it up. That's a percent solution. So if I have a 30% ethanol solution, that would just means that I have 30 milliliters of ethanol. If it's a volume to volume, divided by 100 milliliters of the solution. So see, kind of like capital M, percent, you can convert it to what the unit means. It's always going to be amount of solute divided by 100 something of the solution. It might be milliliters, it might be grams, but it's going to be based on a total 100 amount of that solution. Now, we'll tell you the most common that you're going to see is mass to volume. So mass to volume, if you were in lab and we did the osmosis and diffusion lab, that you had to make up a 10% solution of sodium chloride. So remember, in doing that, you weighed out 10 grams of sodium chloride, you put it in a graduated cylinder, you added enough water so that it had a total volume of 100 milliliters, you covered it up, shook it, dissolved it completely. That was a 10% solution. So if you have what is called a mass to volume, that is because the solute is a solid. So that way you're going to weigh it out in a mass versus using a graduated cylinder to measure it out because it's a liquid. If it's a solid, you'll use a scale to be able to measure it out. So in this, the units for a mass to volume, so like the one over here, so say that I could just say 12.5% NaCl. That just tells me that I have this, 12.5 grams of sodium chloride per 100 milliliters of solution. So that's mass of the solute per 100 milliliters of that solution. So 12.5 grams of NaCl over 100 milliliters of the solution. So that 100 milliliters of the solution includes the amount of salt that's in there. So it's not just 100 milliliters of water, it's 100 milliliters of everything in that solution mixed together. And you remember, that's one of the reasons why I said you've got to make sure you put your salt in first, then add water. Because if you filled it up to 100 milliliters and dumped your salt in, what would happen? It would be above 100, right? So then your volume wouldn't be 100 milliliters. So the rule was make sure you put your salt in first, then add the water to the 100 mil mark, cover it, and then shake it to get it to completely dissolve so that you knew that the 100 milliliters is water and salt that is dissolved. So they're combined as a solution. So what's kind of nice about percent solutions is it's pretty easy to convert them to their units, and you don't have to do any moles to gram calculations. You can just multiply concentration times volume. But in this one, you always want to make sure that you check what the amount of your solution is so that they match. So this one, you need to make a 23.0, and this is mass to volume, so this is going to be grams per 100 mils, glucose solution to feed your baby snakes. Okay, if the final volume of the glucose solution needs to be exactly 200 mils, so that's like 200 with a decimal place, how much glucose will you need? So I want to know how much of my solute do I need? So the rule is concentration times volume. So what does 23.0 mean? Change your percent to what it means. So 23.0% glucose. This means 23.0 grams of glucose, and its volume, so it's 100 milliliters of solution. So just change percent to what it actually means. And now how do I find the amount of glucose? You multiply it times 200 milliliters. Do you see that milliliters and milliliters will cancel? So the unit in the top and the unit in the bottom, that they will cancel. Milliliters and milliliters will cancel, and that tells you grams of glucose. Don't forget to divide by 100. Okay, I see that a lot. Like people go, oh, 23 times 200, there's my answer. Okay, 23 times 200 divided by 100. So what'd you get for an answer? 46 grams. Did everybody get that? Okay, still have calculators. If you need a calculator, still calculators up here to get. 46 grams. Now, going back to my answer, you do have to apply significant figures. So 23.0 has what? This is 3, right? Because remember, zero's after a decimal. 200 with the decimal place is, if there's a decimal place, all the zeros at the end are significant, even though there's zeros in front of the decimal. If there's a decimal, any zeros at the end of the number are significant. So that's also 3. So that means my answer has to have 3. How many does it have right now? Just 2. 46. I need 3. So what do I add? So I would say 46.0 grams of glucose. And if you've ever tried to measure that out on the balance, like when I think somebody had to measure exactly 2.00 grams of baking soda, they were over there going, I can't get it. Okay, it's extremely, like, that starts getting very, very precise. So this is saying not just 46 grams, but you got to make sure that it's 46.0. So it's a much more exact number than just 46. Okay, so see if you can figure out the next one.
Would it be wrong, or why would it be wrong to multiply 23% by 2 because you're doubling the solution?
Well, you could. I mean, if you're thinking of it that way, yeah. But that's still the same thing as saying 23 times 200 divided by 100. And then I've had some students say, like, well, why can't you just move the decimal from 23 to 0.23? Yeah, you could do that too. That's fine. Like, if you think of it that way, just make sure that you include that 100, because that's what you're doing, is you're really just saying, well, I'm going from 100 to 200, so I'm doubling it. But you're just taking the zeros out of play. Yeah. So it just depends on which one, like how your math brain thinks. So it's completely fine. But see, if it was 275, then you'd have to remember to multiply it by 2.75. So that's where it sometimes gets a little hairy. All right, so 12% sodium chloride solution to add to your fish tank. So that means what? 12 grams of sodium chloride per 100 milliliters of solution. And pretty much we're going to stick with the mass to volume ratio. We really don't use the mass to mass or volume to volume very much. So now, how do I figure out how much sodium chloride? Just multiply it times 625. Mass, concentration times volume. See how milliliters and milliliters cancel? Oh, not cancel like that. Cancel. So now you've got to take 12 times 6.25, or sorry, times 625, and then divide it by 100. What did you get? Everybody get 75? Good. Right? So now you know you'd put 75 grams of sodium chloride in, add water to make 625. How much water? Do you know exactly? Nope. Do you know exactly how much water you put in? No, you really don't. You add enough water to make the volume 625, but the salt takes up some of that space, so you do not know the exact amount. So if you were making up a molar solution, or if you were making up a percent solution, you know the exact amount of solute and you know the exact volume of all of it, but you don't actually know the amount of water. You know that you add enough. I add enough water to make the total volume 625 mils. Okay, so there really is no way, because remember how sodium chloride dissolves? So sodium chloride's a crystal. The water molecules surround the crystals and like pull the sodium and chloride ions apart. So they take up less space than they would as a crystal. So there's really no way of knowing exactly amount. You just know you had enough water to make that volume.
How do you know to only do two significant figures with
Oh, well, I should have gone back and said, so 12% has how many?
two?
2.
Okay.
625 has 3. So that's why I left it at 275. I wouldn't round that. Okay. And now remember, like that 100, you don't count that. That's part of the percent. That's part of what percent means. So the 100 mil solution, that's not a measured number. That's sort of what percent means. So the only ones that you would go back and look at is always look at the numbers in the problem when you're trying to figure out rounding. So 12%, I would take the 12. 625 mils, I'd look at those. So always just go back to those numbers. Okay, so you don't know the exact amount of water in molarity or percent. You would just say, I just add enough water to make my total volume, which is 625 mil. The tape. Already with the pen. Okay, that makes sense. All right, physiological saline is 0.9% sodium chloride. Physiological means that this is what is commonly found in body fluids. So this is the salt concentration in your blood. So how would you make up 500 mils of this? So what would you do first? Change your percent to what? Grams per 100 milliliters. Right? And if you want to keep all your words, 0.90 grams of sodium chloride per 100 ml solution. Now I got to multiply it times 500 mils. So see then, mils and mils will cancel. 0.90 times 500 divided by 100 comes out as 4.5. 4.5 grams of NaCl, because that's the only unit left. Is that the right significant figures? So 0.90 is 2. 500 is 1. So I would round that to 5 grams. So you would go to the balance, weigh out 5 grams of salt, okay, put it on the scale, weigh out 5 grams of salt, and then put it in a cylinder. Put it in some kind of measuring cup. Maybe you have a Pyrex, so we're going with something that's got some measuring ability. In lab, we would use a graduated cylinder. At home, you probably have a Pyrex measuring dish or a measuring cup. Like I have one that holds 16 ounces. But on one side, it does give you metric. On the other side, it gives you the English units. But if I was in lab, I'd get something much more accurate. I'd go get a graduated cylinder. You'd need a graduated cylinder that can hold 500 mils. So that's actually one of our tall ones. I hide it from you because I'm afraid you'll break it because I've broken them. So they basically stay in the storeroom unless I need to use them to make up solutions. And they go back there. And when I'm done with them, I'd put it in a measuring container and I'd add water to the 500 mil mark. I don't know how much water, but I know I add enough. I add enough so that the total volume of the solution is 500. I'd cover it with that parafilm, and I would shake it until it completely dissolves. That's physiological saline. So here's an example of volume to volume. So do you see in this one, when you look, there's no grams. Both of your numbers are in volumes. So wine, the percent alcohol in 750, that's a typical bottle of wine. It contains 112 mils of alcohol. So in that solution, 112 mils is alcohol, the rest is water, well, and the flavorings and the colorings and all the other stuff. But you really want to know, if you wanted to know what percent alcohol, which is written on every single bottle, like they have to do, measure that for every single bottle, what would I put on top? 112, right? Because that is my solute. So the alcohol would be the solute divided by the total volume of the solution, which would be 750. So when you do this, do you see you're going to get a decimal? So if you take 0.112 and divide by 750, you get a decimal place. Not 0.112, 112 divided by 750, and I got decimal place 0.49333333, repeating. But what do I have to do to put it in percent? Multiply your answer times 100. So multiplying that by 100, I get 14.9333333%. What would I round that to? See 750, 2 significant figures, 112, 3 significant figures, but I'm going to end up rounding because of 2 significant figures. The 1 and the 4 stay. The next number is a 9, which causes it to round up. So that would be a 15% by alcohol by volume. And you'll actually, if you read a wine bottle, it says that. That's telling you it's a volume percentage, because alcohol exists as a liquid in a liquid solution. Okay, third one. So then again, on your little practice page, there's one there, figuring out how many grams sodium chloride, so you can practice that one. Third one. So the third one is called parts per million or parts per billion. Really, percent is parts per 100. So if you have a 1% sodium chloride solution, that's 1 part per 100. So this is really talking about 1 part per million or 1 part per billion. These are very small amounts, but there are some compounds and even some elements that are out there that in very small amounts can have toxic effects on the body. So parts per million and parts per billion, those are really the most common uses, is talking about how much they have compared to what maybe is a safe level. And here's the easiest way to solve this. Okay, just do this. It does require you do some unit conversions, but you will never get this wrong if you put your mass in grams, your volume in milliliters. So put the mass in gram, volume in milliliters, you divide them, and then you just multiply times 1,000,000 if you want parts per million, or you multiply times 1,000,000,000 if you want parts per billion. Okay, so in this first one, I'm always going to put them in. You look at your first mass, so this one is 12 milligrams. I know I've got to put it in grams. 250 milliliters, that one's good. Right, I don't have to convert that. I want grams per mil. So I have to do one unit conversion before I can do the math of solving this. 12 mg times in a line. What unit goes on the bottom? Milligrams on the bottom, grams on the top. And typically, it's just a single unit conversion. Milli means what? 1,000. Anytime you have milli, 1,000 goes in front of it, and the base unit gets a 1. So this, 12 divided by 1,000, is 0.012 grams. Decimal place goes to the left 3. Divided by 250 mils. So I'm going to take 0.012 divided by 250 mils, and then this I multiply times a 1 with 6 zeros. So I just multiply my answer times 1,000,000 because I want ppm, parts per million. If you see ppm, you know you're going to have to multiply it times 1,000,000. So 0.012 divided by 250 times, and I always do, I hit the 1, then I count 1, 2, 3, 4, 5, 6. Like I always count like the number of times I hit my zeros, because otherwise you're off by 10 okay, or more. Anybody get this? 48. Okay, make sure that you do. I just do the math, I do the division, and then I just multiply that answer times a million. If you see ppb, then you know you've got to put it in grams per mils, and then you got to multiply this answer times a billion. So if it's 0.89 milligrams, I know I got to put that in grams, right? And then I have 12.5 liters, so I know that I got to put that in milliliters. So I have to do 2 unit conversions. I have to convert each one. 0.89 milligrams times in the line, 1,000 milligrams on the bottom, gram on top. So that's 0.00089 grams. 12.5 liters. Liters goes on the bottom, milliliters on top. So this is going to be 12,500 milliliters. Now I'm going to divide those two and multiply my answer times a billion. 0.00089 grams divided by 12,500 milliliters. And I get 0.000000071. Okay? So that's like, there, notice it's a really small decimal fraction that you end up with, but I have to multiply this times a billion. So when I do that times 1 and count, 1, 2, 3, 4, 5, 6, 7, 8, 9 equals. Okay? Did anybody get an answer? I got 71.2 parts per billion. Now some people are like, well, how do you round that? Like, what's the rounding? So typically with this, you get this answer and you're going to end up comparing it to something that is like a threshold. Like the maximum amount of this you can be exposed to is this many parts per billion. Everybody got that one? Did you not get that answer?
I just don't understand it, but it's okay.
Okay, so do you understand how to go milligrams to grams?
Yeah.
Do you understand how to go grams to milliliters?
Mm-hmm.
Okay, so that's where I got those two numbers. So I took 0.89 divided by 1,000 to get 0.0089 grams.
You had to change both of them.
I had to change both of them. And then underneath I took, and I know my 12.5 looks really jacked up. So that 12.5 times 1,000, because that's 12.5 liters, so this should be 12.5. Looks a little better. Times 1,000 gave me 12,500. So I just divided those two. So put your mass in grams, put your volume in milliliters. Whatever that answer is, I'm just going to multiply it times a billion. So that's where I got 71.2 parts per billion. So the important part of this is notice in this one. So copper in drinking water is toxic if it's over 1.3 parts per million. So if you test a 500 ml water sample and measure 150 micrograms of copper ions, is this safe to drink? So if you've ever looked at any water quality testing, like the counties all have to test their water systems. They have to test for stuff like coliforms, which is like, well, that's poop. Like the amount of like intestinal bacteria in the water, it can't be above a certain amount. Same thing. They have to test for lead. You can't have but so much amount of lead in water. It's not safe. It ends up going and collecting in your brain, and then you end up with little mentally challenged children. Okay? So because of that, you can actually go through and list and see all these little ions. Arsenic that might be found in the water, lead that might be found in the water, copper. So if you have a volume of water and you can detect how many ions of copper are there, you can figure out parts per million. So I've got to take, again, just remember, always you want to know grams of the solute divided by mils of the solution. So grams, I see 150 micrograms, so I've got to go to grams. I need to know how many grams that is so that then I can divide it by the volume in milliliters. Do I have to change that? What's my volume? So you see that the volume is 500 milliliters. So that I don't have to do anything to. That one's in milliliters. Just put your units in grams and milliliters, divide them, multiply your answer times 1,000,000 if it's ppm. You'd multiply it times 1,000,000,000 if it's ppb. So I got to do this first one. So now you got to remember that funny little micro symbol. It's still a single unit conversion. I got to put micrograms on the bottom. In front of micro, what do you put? 1,000,000. Remember micro's 1,000,000? Millis 1,000, micros 1,000,000, centis 100. Just go back and look at those ones again. So this is going to put the amount of my copper ions in grams. So 150 divided by 1,000,000, decimal place goes to the left 6 places. So I get 0.00015. If you need a second to put that in your calculator. So there's the mass of my solute. I just take that and divide it by the volume of my water sample, which is 500 milliliters. And whatever my answer is, multiply it times 1,000,000. What'd you get? So 0.3. This is parts per million. So is this safe? Yes. The limit is 1.3. So anything over 1.3 would be considered toxic. So if you come back and you've only got 0.3 parts per million, then yes, it is safe. So try this one. Arsenic. It's toxic above levels of 10 parts per billion, so that's like our limit. Anything over 10 would be considered toxic. Anything under 10, and you're good to go. So if you measure 0.08 milligrams of arsenic in a 7.5 liter water sample, is this toxic? So what do I have to do with my milligrams of arsenic? Convert it to grams. So milligrams on the bottom, grams on top. Milli gets the 1,000, right? So 0.08 divided by 1,000. So now I've got my amount of arsenic in grams. It's very low. 7.5 liters. Can I use that? Nope, I got to go to milliliters, right? So this is sort of like always put your solute in grams, put your solution volume in milliliters. So I've got to put liters on the bottom, milliliters on top. Milli gets the 1,000. Liters and liters cancel, and that tells me how many milliliters. So this would be 7.5 times 1,000, so 7,500 milliliters. Now I'm just going to divide these two. So once you get them in grams per mil, I'm going to divide those, and then I'm going to multiply it times 1,000,000,000, which is a 1 with 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. What'd you get? 6, 6, 6, 6, 6, 7. Yeah, someone was like, can't you just say that? 10.6 repeating. Because if you look at it, it's 10.6666666, and at the very end it says 7. So the key thing, not so much with the significant figures and rounding, but is this toxic? Why? It's above 10. anything above the limit. So it says right here, the limit is 10. So our number is 10.6. So yes, it would be toxic. It is like, or no, it is not safe to drink. And the reason is because this is greater than 10 parts per billion. That's our limit. So you'll always have that in the problem. So that's kind of like your reference value. Solve to figure out what it is, and that way you know. So same again. When you're a little happy. There's a parts per billion question. Okay? So that's the third. So we have molarity, parts, percent solution, parts per million, parts per billion. Fourth one. Okay? Everybody got those? So the fourth one is dilution. So I kind of like their dilution. They changed it a little. But has anybody ever used those little squirt flavor additives? Right? So you buy a bottle of water and people are like, oh, I hate water. Okay? I can't stand drinking water. It's so plain. Okay? Well, yeah. Because it like doesn't react with your taste buds at all. But so they're like, I get these little like flavor additives. And so you just turn the thing up down in like one squirt. So is that little bottle more concentrated or less concentrated than your water? Way more concentrated. Have you ever squirt that in your mouth to see what it tastes like? Strong? Yes, it's like, huh? Super, super strong, okay? So you always just take this more concentrated sample and you dilute it to a less concentrated. So we could say that if this is the initial concentration and the final concentration, which one's always greater? Which one, the concentration? So if I'm looking at the concentration in the little bottle versus the concentration in the glass. In the bottle. So this is always going to be the higher value. The higher concentration. When I add water, that is going to dilute it. So my second concentration is always lower. And you might notice this looks a lot like Boyle's law, right? So remember that was P1 V1 is P2 V2. Well, this is C1 V1 equals C2 V2. So if I take some amount of this concentrated solution, do I use very much of it? No, this is always the lower volume. Because it's that concentrated stuff, then I'm going to add water, and I'm always going to make a larger volume. It's my final volume. So I'll just give you another little analogy in my life. So when I was a kid, and like, you probably, maybe you had this at your grandmother's. When I was a kid, my father used to buy the frozen orange juice in a can. Has anybody ever had that? Okay. So you could buy frozen like Tropicana in it. Well, he would buy like Walmart kind. Yeah. So it was like frozen orange juice concentrate. So it would be in a can about like this. Now, the only ones I think I've ever bought lately is like maybe Bacardi mixers, but other than that. Okay, so it's like in a can, but you know what I'm talking about now? So it's like you can buy like lemonade or limeade in a can kind of thing. So you take it, you open it up, you dump it into a container, and what do you add? Water, right? Because it's concentrated. So you add, normally you should take 1 can of orange juice and add 3 cans of cold water. Well, there were 6 of us in my family. I had 2 brothers and a sister, so 4 children. And like, I always thought like that was normal orange juice. Well, come to find out, instead of putting just 3 cans of water, he'd usually do at least 4, sometimes 5. So I always thought that orange juice was kind of thin and watery. And the first time that I had it in a restaurant, I was like, what is this? It was like so thick and sweet. It was like whole milk versus skim milk. Like, whole milk to me is like, oh my gosh, this is like a milkshake. It's so thick compared to skim milk. Once you get used to drinking it, it was the exact same thing. Because my father was like, well, it lasted a lot longer. Because you kids are eating everything. That, like, I heard that like the entire time I was growing up. I was like, till I had children, I really didn't understand it. So in this, if you're going to do this calculation, you'll always have 3 out of 4 numbers. And the big trick is figuring out what is the concentration, initial versus final, or C1 and C2. What is my initial or final volume, V1 or V2? Figure out which one do I not know, solve for it, plug it in, apply significant figures. So in a large way, this is like going to feel a lot like Boyle's law, but you're just trying to pick out what the problems are. Okay? So skip that one because that one's actually doing a percent solution. We ain't got time. So this one, if you find a bottle of 22.5% magnesium oxide, aqueous, so there I know it's a solution because it's aqueous, so the magnesium oxide is dissolved. How much would you dilute to make 650 mils of 4% magnesium oxide? So what is that 22.5? Is it C1, C2, V1, V2? It's my initial concentration. So that is my initial concentration. Because remember I said the initial concentration is always going to be higher. Okay? You want to make, how would you dilute? So what is that? What don't I know? I want to know V1. V1, I don't know. I want to know how much of that do I need. So I want to know what V1 is in order to make 650 mils. So what's that? I want to make 650 mils. That's V2 of 4%. So that would be C2. Okay, so in each case, identify what the ones you know and figure out what is the one I don't know. I don't know V1, so in my formula, what do I have to move? I don't know V1, so I got to move C1, right? Because see how C1's over on the same side as V1. So remember, if I divide both sides, see how C1 cancels, that moves C1 over to the right side. Remember, it's in the denominator, so it goes in the denominator on the opposite side. Now I just plug them in. So C2 is what? 4%. So we'll keep 4.0% of MgO. V2, 650 milliliters. C1, 22.5% of magnesium oxide. So do you see that the percents will cancel? So percent of MgO in the top and in the bottom. So those units will cancel. And that's going to tell me how much of this 22.5% magnesium oxide I'd use. I don't have to change percent to a number. You can just leave percent as it is. Okay? Just because they're going to cancel as long as they're both percent. And I'm not going to give you molar and percent because that's just mean. Okay, so I will give you those directly. 4 times 650 divided by 22.5. And I got 115.5555556 milliliters, or 5 repeating. Significant figures come into play. What do I need to do? 22.5 is how many? 3. 650 is 2. 4.0, 2. So that means I'm going to keep that 1, 1. What happens to the next? So the 5 is going to go, so it's going to round my 115 to what? 120. So I would measure out, using a graduated cylinder, I would measure out 120 mils of 22.5% magnesium oxide. That's the concentrated. Now, if I'm working with all liquid volumes here, I can figure out how much water. How do I know how much water to add? Huh? No. So if I'm going to take 120 mils of that 22.5, put it in a graduated cylinder, what's my final volume? Yeah. Yep, you just subtract your volumes. So you subtract the final volume minus how much am I concentrated. I can figure out the amount of water you would use in a dilution. Okay, because I'm working with 2 liquids. I'm not taking a solid, dissolving it in a liquid. You don't know how much space that solid takes up. So in this, if I took 650 minus 120, that would be 530 mils of water. Because together, that would make your 650 total volume. Okay? So, bottom of the page, there's two. Okay? 2%, two dilutions. Both of them using percentage. So practice those. If you get stuck on those, I have in Moodle, I already have this done and posted for you. So see where it says Chem 130 practice sheet answers? That's a YouTube video. So it like walks through to solve. So try to solve them first yourself, then you can check them. Okay?
Will your audio like, will be posted in the channel?
You mean this one?